the way I'd like to start, if you notice the title of today's presentation, what you have here and what I originally advertised probably 2 weeks ago is quite different. The reason is the research is evolving so fast, and we're actually doing all kinds of experiments and analysis every day. And last week was a very effective week for us because we were able to take advantage of Fabric and actually did lots of experiments, and we have actually a much better confidence on what we're going to claim and what we have accomplished. Today's talk is based on how to estimate the reliability of power converter, and of course I will explain what is the definition of power converter, and how could you possibly tell that it would last another 1,000 hours, or it would last another 5,000 hours or so. So there is no known technique so far that can actually predict the remaining life of power converters, because it is so complex, first of all, and the analysis is very difficult. And also the question is, how do you measure all these actually characteristics of a power converter that gives you some sort of information? Based on this information, how could you possibly get the overall reliability of the system? So let's get there and talk about what is the definition of power converters and which things fail in a power converter, which are more actually prone to any failure and the most sensitive and most critical components. So a modern power converter would have different types of components, and the definition of power converter could vary, because the power converter used in a solar cell or a solar system or a solar farm would be very different from the power converter that is used to drive the motor. See, in all applications, when we call it a power converter, it means it has to carry power, it has to condition power, or it manages power. So we are talking about power levels in the range of 100 watts to several megawatts. And in a power system, we may have different types of components, such as an electric motor and a power converter, which actually controls the electric motor. And the name of this power converter is, there are two different names, but they're the same. Sometimes we call them variable frequency drive, sometimes we call them adjustable speed drive. But the bottom line is they are used to control the speed and the torque of the motor. And this is a picture that actually shows you what happens when this power converter fails. And this is the picture what shows you what happens when the internal winding of the electric motor fails. In general, this power converter and electric motors, they're very efficient. Their efficiency is a range of 95 to about 96, 97%. But it doesn't guarantee that they are very reliable. In general, motors are very reliable. Like we have seen motors like from the 1940s or 1950s, and they're still running strong. But the question is, there is no guarantee that this motor will last another 10 or 20 years, because depending on the application, they may fail down the road. And power converters, they're not as lucky as the motors, because they fail. Like there are so many premature fails in these power converters. So most of these power converters are subject to electrics and thermal stress, and that's why they fail. In order to ensure failure-free operation, in most applications, we do not connect. Like we just connect the power converter and the electric connection and leave it is there. But in critical applications, such as in a silicon processing fab, you actually a damage or a failure can cost millions of dollars. So in those critical applications, we periodically change or replace all different components to make sure that the reliability is very high. And this process is not optimized, because you never know that the component that you are replacing, how much life it has remaining, or is it worth of replacing it? Because you cannot predict, you cannot see, or you cannot measure according to the knowledge that you have today. This is another picture that happens when you have a damage in a rooftop solar panel, and this is not very uncommon in a solar farm, and probably in a household application. If your wiring is very good, then you may not experience this type of failure. So this is a typical failure. This is called the ground fault failure, which means the chassis or the body of the solar panel is somehow connected to one of the terminals of the solar panel, which means, actually let me explain it. according to this statement. The US National Code, which is NEC, it mandates that the PV panel would have a separate ground than the PV, like the chassis would have a separate ground than the internal negative terminals. This is actually explained here. So it has a system ground, this line, and also it has a chassis ground, which are all these green lines. And there is a fuse in between the system ground and the chassis ground. The question is, these two lines are separate, but how come there would be a short circuit in between? Say there's a crack in the solar panel and water gets into this crack, and it would actually create a short circuit in between the chassis ground and the system ground. And it is very highly unlikely that there would be a crack and water gets into the system, because the solar panel would keep working, but there would be a short circuit in between these two terminals. And what we do to prevent this actually fault, we have a fuse and we have a protection circuit which we call the GFPI, it's ground fault protection and interruption circuit. And in most cases they work, but in some cases they will not work. Because if the short circuit current is less than the sensitivity of the GFPI, it would not trip the GFPI. And in many cases, the fault may occur at night. There is no illumination or radiation, which means the fault current is not high enough to blow the fuse or actually activate the GFPI, and you still have the short circuit current. So what will happen, actually, it will not trip the system immediately, but when you have slight, like at the morning time, you will have some current, and you will have the short circuit current circulating in the panel, and it would actually cause a damage. And because of one damage, and this is actually shown how damage is caused, there is an internal short circuit between one of these terminals and the chassis. And heat is generated in that localized stream of cells, and that can cause a secondary or tertiary fault, which means actually the fault propagates and cause multiple faults into the system. So what can be done? Either we have to use a very smart GFPI system that is very sensitive, but there is actually a penalty of doing that. If you make the GFPI very, very sensitive, then it is actually suffers from noise and provide misleading fault actual indication. And I have seen it. We used in most cases, the GFPI is a differential current relays. And we used a very sensitive differential current relays in one of these electric vehicle charging systems, like what you see today's Chevy Volt or the Nissan Leaf. So I used to work I used to work at Every. I actually looked after an all-electric car back in 2008, and we tested that all-electric car, and we tested with this GFPI circuits. And any kinds of noise, even a noise coming out of a cell phone, can actually be coupled with the GFPI device and make like false interruptions. So that's why we need a system that can detect even a slight short circuit current to the chassis and the intermediate nodes, and at the same time it can detect multiple shorts, or it can detect multiple other abnormal situations in the solar cell. Now the question is, in a big solar farm where we have hundreds and thousands of these panels, how do you find a fault associated with one panel? This is an extremely difficult task, because you need to individually go and measure each panel and find if the characteristics, if it is deviated from the original voltage and current of the solar panel. Otherwise, it would be very difficult, because in a long string, if there are multiple panels connected in series, and you can measure this string voltage where there are multiple panels, and you can guesstimate if there is any fault in one of the panels. And here there are multiple strings connected in parallel, the situation is even worse. So we need a kind of extra vision that you can take an aerial photography of all the solar cells or all the solar panels in a farm, and you can actually find out the location or the grid location at what point you had a fault. And according to the known technology, that cannot be done. And that's why we think we need to actually apply a different technology that is used to detect cable faults. And perhaps you know Professor Sstdr first. She actually had a patented technology called Sstdr, and she developed this technology to detect cable faults in long transmission lines. And of course, how does it do it? So it detects a correlation coefficient, and the correlation coefficient is a function of the characteristics impedance and at the load impedance connected to the transmission line. So using this Sstdr, what you can do, you can measure the impedance in a transmission line or at a point which is far away from you. Now the question is, you can do it using a multimeter, right? And how it would be different? Why we need this state-of-the-art technology to measure the impedance? What a conventional impedance meter or a fluke multimeter cannot do, it does not give you the distance information. So it doesn't give you the idea actually how, like, where is the fault and what is the distance from where you are measuring. So if it happened right here, or if it happened maybe 100 yards from here, so the conventional impedance measurement does not give you this information. Again, the conventional multimeter will not give you the phase information. Then you have to use an LCR meter, because if the load impedance is either capacitive or inductive, the conventional multimeter will not give you that information. And again, if you need both of them, the system will be so complex that it will not be cost effective. So that's why the reflectometry is used in general to detect any fault in the transmission lines, but it was never used in a solar farm, or it was never used in power converter circuits, because the solution or the interconnection between the Sstdr hardware and the power converters would not be that obvious, and there are so many challenges. So let's get the discussion and talk about what are the challenges and how we actually solve this problem. So we tested a couple of solar cells. These are individual group of cells, and there are multiple, like, strings or group of cells connected in strings, and we connected them in series. And we created an intermediate actually fault in the system. So we connected the intermediate node with the system ground or the chassis, and try to measure if the Sstdr hardware, which is shown here, can detect the fault or not. Because in theory, it should detect the fault, and it should give you the location where the fault happened. So this was the schematic that we used. We created, connected 4 cells, 2 strings connected in parallel, and each string would have 2 cells. And we connected the Sstdr hardware across these terminals, and we investigated how it interacts with the system. Now, this is the result we found, the correlated output, the equation that I showed you in an earlier slide. The amplitude versus distance information coming out of this Sstdr hardware, like this is something you get, and there are actually 2 results, PV with ground fault and PV without ground fault, but it shows just one graph. So apparently there is no difference. But if you zoom this waveform and actually zoom that point, you see that they are actually different. So the correlated output was 10,805. This is what, without the ground faults, you get a higher amplitude, and when you have a ground fault, which is the red line, you see a lower amplitude response. So this amplitude difference is sufficient to actually predict that there is a ground fault. And also the distance where it shows the ground fault, it shows that at that location it happened. So it gives you 2 different information simultaneously. It gives you the amplitude, which is a reflection of, or a representation of the kind of fault and how much, or the severity of the fault. At the same time, it gives you the distance information, so you can go and check that at that location there is a fault in the system. We did the test, actually, very recently. We connected 2 lithium-ion cells, which is very common, and the most common types of battery cells. And we connected 2 cells in series. One was good and one was bad. And we were trying to see if the Sstdr system can find the presence of a faulty cell into the system. Because, this is so critical in a hybrid electric car, because there are so many cells connected in series and parallel. So if there is one faulty cell, so it degrades the performance of the battery. And it could be severe. So it could be so severe that the entire stream will fail, such as a laptop battery. there are multiple cells connected in series. So if one cell fails, if there is a single string left, one cell fails, the entire battery will fail. And we were able to actually see the difference in between all good cells and one when the situation is one good cell and one bad cell. And there was a clear difference. The reflection was about 22,000 to 3, 4, and this is 23,000 for photon. So you can actually tell that there was a difference. We also tested a transformer winding when we created a short circuit between adjacent windings. And the Sstdr circuit can detect this, the location and also the amount of short circuit. So we tried it two different transformers. One is an air-cooled transformer, no core, and the other transformer with core. And when there is no short circuit, the reflection data we get about 10,000 or 8,000, depending on the core. But the moment there is a short circuit, and the short circuit may happen at any location of the transformer, so we try to have short circuit at different locations. So we created a short circuit in between 25 turns and 35 turns. Again, like all the time, 10 turns apart. So it's about 35 to 45, 45 to 55. And you can see all these reflections will be very different from a healthy and normal transformer, which means that if there is any short circuit, regardless of the location, regardless of where it happened, and regardless of how many windings they are apart, that the Sstdr system can detect at all. But we have not done yet with this experimental analysis. So basically what we have figured that it can detect the degradation and the failure in solar cells. It can detect the degradation in battery systems. It can detect the degradation in transformers. It can detect the degradation in power converters. But the analysis has been done for power converters, and that's what actually I'll be talking about for the rest of the lecture, actually on today. So we need to understand why converter reliability is so important. Because you see this is a damaged IGBT. This damage with one IGBT can cause a severe failure in the system. The entire system will fail. So this is a faulty capacitor. So these are very real pictures. They happen every day. And they may happen depending on, because of high temperature operation, high voltage and current stress, and any short circuit, any abnormal conditions. This is actually a faulty printed circuit board, so the entire trace was damaged. So there may be different kinds of faults in a power converter. So the converters, the faults could be with the PCB, the faults could be with the capacitor, the faults could be with the semiconductor device. And this actually shows a pie chart that a PCB failure is one of the largest, actually. It's about 26%. The capacitors are responsible for about 30%, and the semiconductor devices are responsible for about 21%. So what things changed, and how the different components degrade. So let's look at capacitors and semiconductor switches. They are the two main reasons for converter failure. And accidental high voltage could cause it. And what happens inside these devices? The MOSFETs on resistance, which is not a critical parameter for low power MOSFETs, but for high power MOSFETs, this is a critical actually feature. We need it always to be very, very low, but with continuous degradation, this RDS or the on resistance would actually change. And capacitor ESR, which is the equivalent series resistance, it will change with time, and the capacitance would actually, the effective capacitance would go down. And the degradation in the contact area, the bonding wire inside the MOSFET or IGBT would actually degrade, and the threshold voltage, transconductance, collector emitter voltage, they will actually be affected with aging. So this aging process, it varies because not all the circuits will experience the same amount of age. It depends on the application of the power converter. If it experiences very high current stress or very high voltage stress or even very high temperature, then actually it degrades faster than a converter which you keep it at room temperature and never overload. So we have seen power converters lasting up to 10 years. And we have seen power converters that fail in 3 months. So it depends on all kinds of things. What happens inside a MOSFET? So actually, I would actually go really fast in the slides because more interesting stuff are on the way. So inside the MOSFET, we may have some cracks and voids. So this is the formation of a crack, and this is a formation of a void, and both things can happen at the same time. And these cracks and voids would actually take place because of any overheat or any over temperature alteration, and of course the current stress and voltage stress. We also have a stress or degradation in capacitors. So this is the equivalent circuit of a capacitor, and this is the ESR that I just mentioned, the equivalent series resistance. And with time, the effective capacitance would go down, and the ESR would go higher than the original capacitor. So this is a healthy capacitor, or a group of capacitors. They're all unique. And you can see a puncture or a presence of the liquid that's coming out of the capacitor. So definitely has gone to a very high ambient temperature or very high voltage or current that actually causes this leak and it bursts. And also these are all damaged capacitors. You can see all these cracks and bursts, damage that happened in this capacitor. So what happened, if you operate the capacitor at very high temperature, and if there is a crack or void, all the electrolytic solution will evaporate. And with this evaporation, what will happen? Of course, the ESR will go up, and the effective capacitance will go down. So the purpose actually for using a capacitor, it's canceled. Like you need a capacitor in a system to rectify or condition the voltage, and you don't get it anymore. And what things cause this capacitor failure? The high voltage, transients, reverse bias, vibrations, and high ripple current. And all these things will add up and degrade the performance of the glass. Now, why we need a state-of-the-art solutions? Why there is no known technology? Because power converters, first of all, they would not be used in that many volumes that we use in today's market or today's life. Like everything is becoming electrical. The cars are becoming electrical. And we see all kinds of renewable energy sources. So the journey of electronics, power electronics, when it started maybe 30, 40 years ago, it's a relatively new area. And we never cared for the reliability of the system. And we knew that they're failure prone and they need to be replaced every 5 years to 10 years. But the question is, it was never questioned that, is it worth of replacing the power converter? So first of all, there was not such a strong motivation. But these days, we are using power converters in such critical applications that we need to make sure that when we're replacing a $1 million power module, it doesn't have any line. We need to make sure. There are a couple of techniques actually. In most cases, they take the power converter and if they suspect that the capacitor is failing, they take the capacitor out and measure it individually and try to replace the capacitor. So this is one way to predict the reliability because the capacitor is one of the most failure-prone devices in the system. In many cases, they actually measure the MOSFET or the IGBT individually and try to guess the reliability of the system. But there is nothing, actually no technology that you can connect to the system and get all the parameters at the simultaneously at the same time. Of course, there are other techniques that actually measures the voltage and current that the converter is producing. And from this voltage and current, you look for a signature. And the signature actually represents any failure with the circuit or a failure with the component. But in most cases, it is very difficult to pinpoint which component is causing this problem. But using Sstdr, the biggest advantage is you can look at the signature, but at the same time, it gives you the distance information. So you can actually locate which component is failing. So what would be our vision? Our vision is the future power converters. This is the power converter. It has 3 inputs, line 1, 2, and 3, and 3 line outputs. So this is what would be the biggest application. The biggest application would be a motor drive. So if you connect a 3-phase AC system to the motor drive, and this is the outputs that are going to the motor. So by changing the duty ratio in the circuit, or by controlling the circuit, you can actually change the speed and the torque of the motor. Now the question is, how do you predict that which component is failing? Now look at the circuit. Like if you need to characterize this component or this IGBT, this component is called IGBT, this is an insulated gate bipolar junction transistor. So what you need, you would probably need the access to this point, and measure the component. And interestingly, these 2 points are already accessible in the power converter. You do not need to create an intermediate node because this point is the DC bus, and this is accessible. And these 3 inputs, these are accessible as well because you connect them to the 3-phase system. And these 3 pins, they are accessible because they go to the actual motor. So to characterize individual components into in this circuit, you do not need an intermediate nodes. So we envision that the future power converters will come with a socket or some sort of an interface. And these interfaces are necessarily the same pins here, the input power or the output power. And we connect our Sstdr system across these points and we see some reflections. And based on the reflections, we can predict which component is fading or which component has a degradation rate higher than the other components. So these are the actual setup. So in this setup, we are testing one MOSFET, and in this setup, we are connecting a data acquisition system with the Sstdr hardware, and this is also connected to a circuit. So this is the basic circuit. We are testing the MOSFET here, and we are not measuring the RDS using the Sstdr. We are measuring the reflection in between drain and source, and the RDS is being measured by the data acquisition system. So these are the experimental data we have received. We had 4 or 5 MOSFETs, and 4 of them are aged. Aged means we actually put it in a thermal chamber, and we put huge thermal stress on these MOSFETs, and we try to see if this thermal stress actually caused any damage inside these MOSFETs. So for all this, for the new MOSFET, the RDS was 44 milliohms. Just look carefully at this value, which is 44 milliohms before aging. So before we did any aging, this was 44 milliohms. And M2 was very lightly aged, so the RDS went up a little bit. And M3 was moderately aged, so you can see it's 43.95. I imagine this is a glitch in the system, so we could not measure it completely. But the reflection, we have seen it. When it is heavily, I'm sorry, I'm actually looking at the wrong column. So RDS, before aging, it was 44, but lightly it is 45, so it went up. When it is heavy, it's 51, and it progressively goes higher and higher with higher level of aging. So definitely this is one good way of looking at it and predict the remaining life of the MOSFET. And we have a rule that if it goes more than 20% or 30% of the original value, then we can say or we can claim that this is at the end of its life. And we also observe the variation in the reflection coefficient because we started with 22,847. We ended up with 645. So you can see there is a significant amount of variation in the reflection coefficient, which means, yes, you do not need the RDS measurement scheme, but if you use the Sstdr scheme, and you can actually see the variation in RDS. We also did the experiment with capacitors, and these are the ESR after aging. You can see we started with 197. And with higher and higher aging, we measured the ESR between 208, 223, and 220. And also, we have observed a variation in the correlated output. We started with 20,000, but we ended up with 19,000, so it dropped. And this is something we have seen with IGBTs. And we measured the RCE, or the collector emitter voltage, collector emitter impedance. It was 35 milliohms, went up to 36 or 60 milliohms with aging. And also we observed the variation in correlated output. We started with 21,000, we ended up with 20,000. So what is the trend we are seeing here? We are seeing that with higher level of aging, our correlated output will go down. Now the question is, how do we correlate it with RCE or with the ESR or with RDS. Of course, the correlation would not be the same. So that's why we have plotted it. You can see for MOSFETs, this blue line is actually the on resistance, the RDS, and when it goes up with aging, our reflection data would be higher. And also this the capacitor ESR, you can see, and on this scale, the higher means actually the amplitude is becoming smaller. So with the capacitor, when we lose capacitance or the ESR would go up, and of course our reflection data would go up, but with a smaller magnitude. And this is the same for IGBT. So we can safely claim that the Sstdr can actually detect the degradation in all these three components. Now the question is, we can characterize individual components, but how useful this is? How could you possibly get the actual reliability of the entire circuit? And now you need to know the actual circuit diagram. You need to know the architecture of the circuit. You need to know how many MOSFETs are there. Because if there is one MOSFET and one capacitor needs the degrade, then actually the circuit will fail immediately, or that it's so severe. Now, if there are 4 MOSFETs and 4 capacitors and one of them is degrading, then definitely the severity is not as high. So you need a modeling, or you need a circuit modeling, and you need actually a reverse mapping technique, and that's actually being shown here. Severity. This will become a little complicated. This is an H-bridge circuit, and this is a DC to AC converter. So the RL is receiving it's actually seeing AC voltage across DC terminals. And we are applying a DC voltage. So this is a DC to AC converter. Simple. Now it has 2 states. In state A, this transistor and this transistor will be activated. And in state B, this transistor and this transistor will be activated. So in 2 states, you have 2 equivalent circuit models. Now, we actually measured reflection across each node here. So 1, 2, 3, and 4. So when we have 4 nodes and we are measuring 2 nodes at the same time, then you have 16 possible combinations. That's what you see here. So 1, 1, 1, 2, 1, 3, and 1, 4. So in this way, 2, 1, 2, 2, 2, 3, and 2, 4. Now the question is, 1, 1, which means you are connecting the 2 terminals of the Sstdr across the same point or the same node, which means it doesn't give you any information. It's just a short circuit. In the same way, X22 is the same. X22 is the same, and X44 is the short circuit. But the other nodes, or the other impedance measurements will give you the impedance discontinuity or continuity across each and individual node pairs. Now, if this MOSFET starts to fail, or if it has higher impedance compared to the others, when it is on, you will definitely see some variation in between 1 and 2 compared to 3 and 4, or compared to 3 and 1. It's very different. That's what we're trying to build, the impedance matrix here. Now the question is, what we need is the individual component parameters such as RDS1, RDS2, RDS3, and RDS4, or we need to know what happened here, what happened here, what happened here, and what happened here. But when we take the measurement, we do not measure the individual components because all of them are connected with each other. So we get the matrix, but we need this individual data. So that's why we have a nonlinear operator that actually maps this impedance matrix and gives us this impedance vector. Now we compare, and these are actually some real experimental data that we show that once RDS1 was affected, how it changed, how the impedance vector changed. So you can see that here it was 0.04 and it went up to 0.05. It was 0.04 and it was 0.05, and the remaining components were the same. And now, how these impedance matrices were affected by these variations and individual components. So we use the least square method to figure out what was the actual solution, and we can see that the error function becomes the smallest when we try with the correct data, which was 0.05, and you can see that here this was 0.05. It went from 0.04 to 0.05. And when we try with 0.05, we get the minimum error. So why we did that? Because there is no way you have the impedance matrix and you can come here. Because this is a nonlinear system, so you cannot take the inverse of this matrix and comes to this vector. You cannot. So the conclusions is we have done different kinds of testing with different types of converters, different types of other components such as electric motors, transformer windings, solar panels. And we can see that the Sstdr can detect these failures. The question is, how do you know the reliability, or how do you know the remaining life of the system? Then you need to actually do this nonlinear analysis and get the impedance matrix first. Do actually put the system model here, all these nonlinear equations, and come to this impedance vector. And then you can predict if there is any failure in RDS1, RDS2, RDS3, and RDS4. You put it in another model which talks about the remaining life of the circuit, but we are still working on that. My students are working on this, the future model that actually takes this degraded data and puts it into the model and predict the remaining life of the system. So Sstdr was applied to PV cells, battery strings, electric motors, transformers, and power converters. Sstdr is applied in single-phase DC AC converter between different test pairs, and we work with the corresponding output for different pattern impedances. The test results suggest that this technique could be used to identify the aging in the entire power converter. So that's what we are working on right now. We first verified that the Sstdr system can detect the degradation across individual components, and now we are working with individual data and put it into a different model, and that model is very much converter specific, and that gives you how long this converter will last. And we, of course, we are trying to follow a technique that's based on, we take a new converter and we take a used or aged converter, and we actually measure or compare the characteristics of these two, and this impedance vector that I showed you. So definitely a new converter would have very different impedance vector from the one that is already aged. So the RDS1 involved associated to a new converter and new MOSFET would be very different from the RDS1 in an aged converter. So once you know the variation across individual components and compare it with the original or the new converter, then you can possibly tell that, okay, it has degraded over the time that much amount, and it would last another 5,000 hours to 10,000 hours, considering everything is normal. Thank you so much, and I would like to have questions from you.
Thank you. Questions for Faisal?
You are reporting out to, in some cases, 7 decimal places on that measurement system. Have you done any verification of the measurement system itself for its repeatability and its reproducibility for decimal places that far?
No, that's a good question. Let me open the presentation. Sorry, that was.
I was exactly the same question, by the way.
Yes, let me answer that.
Actually, there are 2 types of repeatability. One with the same system, if this one had it and this one had it, and see if you get exactly the same measurement. And then a similar system with the same fault, does this signal go down, like in that case, does it go up instead? So you know what I'm trying to say, it's the same kind of behavior.
Typically in industry, we would run a gauge R&R on the station to see if it's person related or measurement system related for repeatability. Those decimal places are
no. Actually, I should have clarified. These are the measured data, but sorry, this one is a test case when we actually changed the circuit parameters here. So let me tell you actually what we did. We actually assumed values in these different components, and these are the values that we get as a result of series and parallel combination of the circuit. These are not test data, that's what I'm saying. This is an analysis, and this error analysis was done based on the model or the different components. So this is not the test data, and we have not yet compared these analytical values of the test data. But the test system is fairly sensitive. That's what we have seen, and it's very, very repetitive.
But earlier in the presentation, you were expecting basically a 1 to 6% change, roughly, from an aged MOSFET to an aged FET to a non-aged FET, right? Your chart that you showed. Yes.
Slide.
This slide.
Yes. So we started with 44 milliohms and we ended up with 64. And the corresponding reflection was like pretty measurable. It was 645 and this is 847. So it's about 100 deviation or a deviation in maybe 20 milliohms. It's quite sensitive. And it was very repetitive. We have done this testing many times. Because we are doing the system testing at very high frequency, the resolution is quite high. So we see a significant variation. It starts from, it's a spread spectrum. So we start from 12 megahertz to 96.
96 megahertz.
And then was your circuit live?
Yes. These are live. These are functional because
But you were actually powered up and
yes.
cycle in between?
Yes. And this high frequency does not interfere with the operating circuit or frequency of the circuit because in power circuits, in most cases, they're very slow compared to this testing frequency. Yeah, if the MOSFET is off, you cannot actually measure it because if there is no current path, the RDS will be infinity, so you cannot measure it. So of course, this is a live system.
Yeah, I don't know if you're measuring something intrinsic in the pole, but okay.
Any other question for Faisal?
I think it was not that interesting work. I made it in a very good.
Story made it very clear.
Well,
What distracted me was your first, actually, the second one was last where we had the graphs. And really see the difference, just a little peak there.
Yes.
And we're still using it. Is it always like that? So if you look at that thing, actually not even way before now,
The actual
keep going.
reflection.
Yeah, the actual reflection graphs, the very beginning.
Yeah. Which one? This is for the batteries.
There's a one. Yeah. So is that the only always difference? Is that always the same? So if you disconnect everything, reconnect everything,
Yes.
exactly the same.
Yes.
Is that kind of
It is very consistent. It is very consistent. And just, I think I skipped that point. The hardware that we are using, the Sstdr hardware, it is not optimized for this type of applications. It was designed for transmission lines. So we are simultaneously modifying the hardware. So we expect to see better resolution, better accuracy this time because the hardware was designed for very long distance transmission lines in hundreds of thousands of feet. Like we are looking at very close proximity. So far we are getting great results. So we are hoping that we need to be optimized for these of these applications. Then it will give us better results.
So was your fault 50 feet away?
Yes, because the cable length was about 50 feet.
That long?
Yes, because this comes with the hardware. You have to have cable that way.
What if it goes in higher?
Yes, we can, but the hardware actually does not allow that. So that's what Professor First and I'm working on, how to actually modify this hardware to apply with these applications, using these applications.
Any other questions?